In the previous video, we talked about chemical nomenclature and the rules by which chemical compounds are named. In today's installment, we're going to dive into VSEPR theory. At the end of the day, VSEPR theory is basically a tool chemists use to predict the exact shape of molecules and polyatomic ions. We've already discussed Lewis structures, which show us the valence electrons and bonds between atoms. But these structures have one major and glaring drawback. They don't show us the exact shape and structure of molecules. They don't tell us anything about how atoms are arranged once they have formed bonds. For example, here we have two possible Lewis structures for a water molecule. In the real world, do individual water molecules look like the drawing on the left or the drawing on the right? We really have no clue because Lewis structures alone don't give us that information. Now let's put a definition to molecular geometry. Molecular geometry describes the exact shape and structure of any given molecule. Remember, we're talking about molecules here, and in the broadest sense, this includes polyatomic ions too, since polyatomic ions are made up of more than one atom. We've already looked at atomic structure. Today we're looking at molecular structure. Just another way to think about it. Our primary tool for studying molecular geometry is the valence shell electron pair repulsion theory, also known as VSEPR theory because its longer form is quite the mouthful. VSEPR theory tries to predict a molecule's geometry by looking at its electron pairs. This is the fundamental idea or postulate of VSEPR theory. Electron pairs are repulsed by one another, so they want to stay as far apart as possible. For the purposes of VSEPR theory, electron pairs include both bonding electrons, or electrons involved in bonds, as well as lone pairs or non-bonding electrons. Whether they are involved in a bond or not, electron pairs don't want to be near each other. Down here, we have the most accurate Lewis structure of ammonia, which has the formula NH3, according to VSEPR theory. In a molecule of ammonia, there are two non-bonding valence electrons on nitrogen, making one lone pair. In addition to this, there are the three electron pairs involved in the covalent bonds between nitrogen and these hydrogen atoms. This arrangement maximizes the distance between the electron pairs, so this is the predicted molecular geometry of ammonia. VSEPR theory also predicts the angle between the bonds that hold a molecule together, and this angle is referred to as the bond angle. In this case, there are two bond angles. One lies between the bond with the top hydrogen atom and the bond with the leftmost hydrogen atom, whereas the other one lies between the bond with the bottom hydrogen atom and the bond with the leftmost hydrogen atom. These two angles should be equal. Here's another example, the accurate Lewis structure for water according to VSEPR theory. This time there are only two bonds, so there's only the one bond angle between them. It's also worth mentioning that bond angle is the primary factor when determining the shape of a molecule. This is because drawing accurate Lewis structures requires some knowledge about how the atoms are arranged, and knowing the bond angle can help us predict that and draw the best structure possible. So, what determines bond angle? Bond angle is determined by two factors. Firstly, we have the number of atoms bonded to the central atom. The central atom is the atom with the lowest electronegativity, the atom that the other atoms in the molecule are attached to. In ammonia, for instance, nitrogen is the central atom because nitrogen is less electronegative than hydrogen, and all three hydrogen atoms are bonded to the nitrogen atom. For the purposes of our discussion, we'll call these other atoms surrounding atoms because they surround the central atom. Secondly, we have the number of lone pairs, or non-bonding electrons, on the central atom. The sum of these parameters, by the way, is called the molecule's steric number. Alright, this is where we get into the technical details behind VSEPR theory. This table summarizes some of the common molecular geometries encountered in a typical general chemistry course. As always, this comes with the standard disclaimer that this is not a comprehensive list. There are actually many more complex molecular geometries that are not on this table. Some classes may choose to cover these more advanced geometries and others may not. So for simplicity's sake, the more advanced shapes have been omitted here. It's very easy to find longer lists of molecular geometries though, so if that's a concern for you, it shouldn't be too hard to find what you're looking for. If there is popular demand, I can also put together a table of more molecular geometries than are listed here and post that on my website. So if that's something you'd find helpful, leave a comment and let me know. Let's scroll down a bit. There, that should be the rest of them. 9 common geometries in total, but again, this is not a comprehensive list. From this table, we will notice that different molecular geometries come with different bond angles, and it might be useful to memorize at least a few of these. This was something that didn't fit in the original table, but is important to talk about anyway. Here are some examples of molecules that fit each molecular geometry. A diagram of each is provided as well. Carbon dioxide has a linear geometry and is drawn like so. Then we have the 2 bent geometries, represented by sulfur dioxide for the bent geometry with 1 lone pair, and represented by water for the bent geometry with 2 lone pairs on the central atom. Over here to the right, we have boron trifluoride, which has a trigonoplanar geometry. These last 5 geometries now, these have a special feature. Instead of being represented by their own Lewis structures, the trigonal pyramidal, tetrahedral, seesaw, trigonal bipyramidal, and square pyramidal geometries are represented by these 3-dimensional diagrams called structural formulas. These are similar to Lewis structures, but with one key difference. Instead of using straight lines to represent all bonds, these 3D structures take the 3D reality of molecules into account. Molecules are not 2-dimensional structures, which means that we can't draw them on a piece of paper and assume that those kinds of drawings are representative of reality. To represent the 3D structure, these diagrams use 3 types of lines. The regular and straight lines represent bonds that are on the plane of the paper. The filled-in triangle on the bottom here represents a bond that is going into the page. And the dashed lines up here represent a bond that is coming out of the page and towards us. This type of 3D diagram is very common in organic chemistry, so it's useful to at least introduce them now. It's also an opportune reminder that molecules are in fact 3-dimensional. One important note. We have to remember that the bond angles written in our table and represented in these drawings are ideal bond angles. Because real life is rarely ideal, however, many real molecules have bond angles that are slightly different from the ideal values given here. The difference can be as large as 5 to 10 degrees in some cases. So if we look up the exact bond angles of some of the molecules up here in a textbook or someplace on the internet, we shouldn't be surprised if the actual bond angles are a bit different than those listed. Another way to say this is that the ideal bond angle provides the maximum distance between electron pairs, but real molecules don't always take full advantage of these ideal arrangements. Quick recap. Lewis structures help show us the valence electrons and bonds of atoms, but they do not tell us anything about the precise 3-dimensional structure of atoms involved in a molecule. VSEPR theory fills that void by using the positioning of electron pairs to help predict molecular geometries. The theory assumes that electron pairs, whether bonding or non-bonding, want to be as far apart as possible. They repel one another, in other words. Molecules are arranged to maximize the distance between electron pairs, and bond angles serve as a parameter to measure this distance. Determining the molecular geometry of a molecule demands that we look at two properties of said molecule. First, we need to count how many lone pairs are on the central or least electronegative atom. Second, we need to see how many atoms are bonded to that central atom. With these two numbers, we can refer back to our table, or another more comprehensive table as the case may be, and predict the molecule's shape and structure. Three examples before we close. Example 1 says, use VSEPR theory to predict the molecular geometry of beryllium difluoride. We can approach this problem by drawing the Lewis structure of beryllium difluoride and using that to count up its lone pairs and surrounding electrons. We should recognize at a glance that beryllium is far less electronegative than fluorine, so the Be is going to be our central atom. Beryllium has 2 valence electrons, and it is bonded to 2 fluorine atoms that each have 7 valence electrons. This means that both of beryllium's 2 valence electrons are going to be bonding electrons, so our central atom is left without any lone pairs. We don't care about whether the valence electrons on fluorine are bonding or not. We only care that both fluorine atoms are bonded to our central atom. So then, we have a molecule with 2 surrounding atoms, and 0 lone pairs on the central atom. From our table, we see that beryllium difluoride has a linear molecular geometry. Example 2 is similar. Use VSEPR theory to predict the molecular geometry of carbon tetrachloride. This problem is bringing in some of what we covered the last time we were here. From what we learned about chemical nomenclature, we know the chemical formula of this compound is CCl4. If you're confused at all about this, go back and watch the previous video. It should help you out. Chlorine is a halogen, and carbon is not, so we can essentially assume carbon is less electronegative and is the central atom. Carbon has 4 valence electrons, and each of the 4 chlorine atoms has 7 valence electrons. If carbon shares 1 valence electron with each chlorine atom, all 4 of its valence electrons are going to be involved in bonds. The number of lone pairs on our central atom is therefore 0. And there are 4 atoms total bonded to said central atom. Referring back to our table, we notice that 4 surrounding atoms and no lone pairs corresponds with the tetrahedral molecular geometry, so that becomes our final answer. This last example is a bit more conceptual. Example 3 asks, why do you think VSEPR theory is designated as a theory? We don't have to think too hard about this one. Remember, VSEPR theory is founded on a single major assumption. It assumes that a molecule's geometry is determined by the repulsion between electron pairs. This is a good and logical idea, but it's not perfect, and the VSEPR model isn't perfectly accurate in predicting the real shape and structure of every single molecule in the universe. It's always possible that VSEPR theory will be modified, added to, or even completely or partially disproven in the near future. That hasn't happened as of yet, so it's still a good model to use when predicting molecular geometries, and this is why a lot of chemistry classes continue to emphasize it. In the next video, Unit 2, Video 6, we will delve deeper into polarity and how it relates to what we've learned so far about molecular geometry. Thank you for watching.